Are there any questions before I switch the iPad? So remember, today we have another quiz at the end of class, so like around like the last 30 minutes. But yeah, we can talk about that once we get closer to this. So basically the plan, let me switch to the iPad. Wait. So the plan for today is just to talk about trigonometric functions and a lot of limits involving trigonometric functions. So like from yesterday, for now, like the most important thing that you have to remember about trigonometric functions is that if you have the unit circle, so this is like what I said last time. If you have the unit circle, x squared plus y squared equals 1. And then you have this angle of theta. Then the entries of this point on the circle, which is x comma y, is actually the same as cosine of theta, sine of theta. So the cosine is like the horizontal coordinate of a point, and the sine is a vertical coordinate of a point. So the cosine theta is the horizontal coordinate, or the x coordinate, and the sine of theta is vertical coordinate, or the y coordinate. Is that making sense? So yeah, basically the most important, like really of things involving sine and cosine, that's like the most important thing of how sine and cosine are related to a right triangle and also to the unit circle. Okay, and so in fact with that you can the idea is like you can think, well, this is why this notation is used, right? If you write something like sine of theta and cosine of theta, right? You can think of these as depending on theta, so you can consider these as functions of theta, right? So can consider these functions of theta. And since they're functions of theta, you can think of what their graph should look like. Okay, so there's actually like a cute way to figure to find out the graph, like in terms of like an animation. I mean, I will show you like a couple of ways, but I imagine most of you have already seen it before, so like I'll just show you what this looks like. Let's see. Let me go. Okay. So here's like, for example, it's easier to visualize the graph of sine. You'll see why in a second, but you can go. Yeah, so if you go to my like website, you actually will see that I have a couple of like animation. So there's like this animation about the sine and the unit circle. So if you pay attention to this, like I'm moving an angle on the unit circle, right? And remember, the sine is the vertical coordinate. So the sine is the length of this purple segment that I'm showing you here. So I don't know if you can see it, right? But if you keep track of, let's just wait for it to return. So if you keep track of this vertical segment, right? It starts at 0, it keeps growing until it gets to the North Pole. Then it goes to 0 again at the equator, right? And then it becomes negative. It grows in the negative direction until it goes to the South Pole, and then it goes to 0 again. Is that making sense? So like here, I'm just showing you like kind of like putting like all these vertical bars together, and that's how you end up getting the graph for sine. Is that making sense? Sort of. It's like a fun way to think about how to find the graph of the sine function. So it's really literally just keeping track, of like these vertical segments, how they're changing as you change the angle. Are there any questions about this one? So, and then like just to go to GeoGebra, the thing is like on a circle, right? If you keep walking on a circle, you return to your starting point, right? So you like this pattern would repeat itself forever, right? That's why you say that the sine function is periodic, because it returns to the same place eventually. So that's why when you like graph the sine of theta, I mean for GeoGebra you have to put it like sine of x. That's not too important for now. You see, like you get what I was showing you here, but then let's see. So you get like the stuff between x equals 0 and x equals 2 pi. That's like what the animation was showing you. But then you just repeat this, like, kind of copy paste this graph um, to the right and to the left, and that's how you end up getting like the full graph for sine of x. Is that making sense? And then for cosine of x, it's kind of like a similar idea. You would just need to keep track of the horizontal segment, how big these horizontal segments are. And so if you put cosine of x here, it just it looks very similar to the graph of sine actually, but it's actually shifted. So one way to find the graph for cosine is just kind of take the graph of sine and translate the graph by a certain amount to the left. So yeah, these are kind of very useful functions to have, because they are related every time that there's some motion that is repeated. Because again, sine and cosine, the very particular property that they have is that they return to their original value. Okay, and that value of repetition is called the period. Is that making sense? I'll kind of draw a little bit the graphs for sine and cosine in a second on the iPad, but I mean it's more like just kind of like have like some idea of how they look like. But that's the basic thing. Okay. So let's see, in fact, if I can show you this. And in fact, like, so yeah, like what I was saying is like the thing, sine and cosine appear in many places. So for example, if you go to GeoGebra, you can enter Hooke's law. Hooke's law is just like the law for the force that's acting on a spring. Okay, so you can have like you can have something like this, like a mass attached to a spring. So Hooke's law tells you like what the force is. The important thing, if you look at this animation, right, is that this mass, this piece of wood or this block kind of returns to its original position after some time, assuming that there's no friction and other things, right? So that tells you that the position is kind of like oscillating or returning to a starting point, right? So if you think about it, there's like a periodicity in what's going on, because like after, if you wait long enough, the math will return to its original position. And so actually that tells you that there's like secretly like a sine or a cosine involved in this problem, because those are actually the functions that are used to describe things that repeat themselves. So a cute way to see that show up is there's like this animation in in an MIT physics class, which is very cool. Oh, let me see. He's got like, so he has like a spring can that is you see like going back and forth. It's kind of like the analog of the spring with the mass that I showed you in the GeoGebra thing. So he's putting there like that. Let's see. Okay, so that's oscillating, right? So it's going back and forth, and if you just move it, like move the piece of paper around, like that's kind of like introducing like a time variable, and so you see you get like the sine function. So like there was secretly like the sine function hidden in the problem, and wait, that's like a fun trick to make it show up in the animation. Okay, but well, all these things are just for you to remind everyone that sine and cosine are actually pretty important. So that's why we're going to spend a little bit of time just like studying certain limits that involve those. Okay. So yeah, sure. This is the only thing I have written. So let me show you, like, let me just at least write the draw the graphs for sine and cosine. Again, so the graph of sine, the idea of sine, if you remember from the animation, it starts at zero at an when the angle is zero at pi at 90 degrees or pi over 2 radians. I'll write the angles in radians. Like usually, um, most of the times in this course, like the angle will be in radians. So I'm writing the important thing of the curve for sine of theta. And the reason why I'm doing the other like a little bit broken is just to I again emphasize that it kind of repeats itself. So like once you understand sine between 0 and 2 pi or 0 and 360 degrees, um, then you kind of understand the sine function everywhere. Okay. So and here is -1. And the one for cosine of theta is very similar, but again, it's kind of shifted a little bit. So, you can have 0 pi over 2 again, pi, 3 pi over 2, 2 pi. So at 0 is 1, it becomes, oops. I don't know. Okay, this is trying to make it like a line. Okay. Um, oops, take it back. Oh yeah, yeah. It was fine before. It's no, it's good. Yeah, this one looks a little bit worse, but this is also between 1 and -1. Okay, so this is a graph of cosine. And again, after that, it just repeats itself. So like I won't even try to finish it. You just like complete the graph there. So. In fact, for calculus, the two of the important, like one of the important properties for calculus is that sine and cosine are always between -1 and 1, if you look at the graph. Um, so so this is like going to be very important for us. You'll see, we're about to use it in a couple of minutes. So this is very important. Sine of theta is always between -1 and 1, and cosine of theta is also between -1 and 1 for all values of for any value of theta. Is that okay? Is that making sense? Um, okay. So let's try to see how this will be used in practice. So for that, let me tell you something else, which is called the squeeze theorem or the sandwich theorem. And once we have that, we can start applying it to this sine and cosine things. You'll see why it's called that in a moment. So the idea is that if you, let's say you had three functions, f, g, and h. Oops. Okay. So here's what the squeeze theorem says. You have a point A here, and the squeeze theorem says if you know that okay, if near A we have that g of x, is between f of x and h of x, right? So if you know that this is why it's called sandwich theorem, because, or the squeeze theorem, because you know that near this point, the function g, oops, sorry about that. You know that the near this point, the function g is squeezed between these two. Just give me a second, sorry. If you know that the function g is between f and h, then it is being squeezed between the two, right? So what the what the squeeze theorem says is that if somehow you know that if you somehow know the limit for the extremes, and that limit is the same, then the limit for the middle has to be the same. So let me write that down. Let me zoom out here. So I don't know if this is making sense. So what the theorem is saying is that if you know that you have like any L is a value of the limit. Sorry, I should put here L. This is the value of the limit. Here L is the value of the limit. So it is a number, right? Because the value of a limit is a number. So what this is saying is that if you have an inequality and the extremes of that inequality have the same limit, that forces the one in the middle to have the same limit. Is that making sense? So I could actually draw L here in the picture. L is kind of this value that you see here, right? Is L is here, because that's a height where like the curves would meet, kind of. Is that making? I don't know if that sounds. It seems better now. So again, like it is like it's called sometimes a sandwich because you imagine like the F and H as like the two pieces of bread, and then the meat or cheese or whatever like inside the sandwich is like this thing that's being like it's in the middle. So if you're taking your two pieces of bread, you're going to like make them pass through the same point in space, then everything that's inside of it has to go through the same point in space. So it's kind of like if the two pieces of bread kind of there would be taking the same value the moment you kind of are trying to slam them through like a door or whatever, and then like the whatever is inside has to go with it. So it's kind of being dragged, you know, it's kind of being dragged with the rest of the bread to take whatever value it wanted to take originally. Okay. Okay, so just to better to give you like some application so that you see what the flavor of the squeeze theorem is. I mean, what the point of the squeeze theorem is. So here's an idea. So here's an application, or like first, like let me start first with an example, and then I'll give you like an application of this. So this is like a tricky question. So yeah, let me give you 1 minute to think about it, maybe. So what would you say the answer to this is? Ooh, good, good. Right. You're saying that it shouldn't exist, and I agree with you. And why would you say it does not exist? Or someone else, like let's say who, if anyone wants to comment. So remember, this was perfect. Yeah, yeah, yeah. So if you look, if you remember, this was the graph of the sine, right? Like the horizontal axis is the angle. So if you make the angle go to infinity, right? If you keep changing the angle, what's happening with the graph? The graph is just repeating, it just repeats forever and ever, which means that the graph always goes back and forth from, -1 to 0. Oh, sorry. Yeah, -1 to 0 to 1, and then 0, 1. And, it always oscillates between -1 and 1. Is that making sense? The limit should be, for the limit to exist, all the values need to the values of the function need to be approaching a particular number, right? So in this case, for the sine function, it never approaches a particular value. Is that making sense? Of why the limit shouldn't exist? It's just because it keeps oscillating for eternity. Is that clear? But now let's compare this with something different, which is going to be so I'm going to take the same function, sine of x, right? Well, it should be sine of theta, but again, in GeoGebra, like the variable always has to be x. So instead of taking sine of x, I'm going to divide that by x. Okay. So now you have here the one that you see in orange, right? Which okay. And so what's happening with this function? So if you look at let's zoom out. It's actually changes quite rapidly. So if you look at the graph of this function, it kind of still is trying to oscillate, right? If you see it, like it still goes up and down, up and down. So it has there is a sense in which it tried to repeat itself as a sine was, but now kind of like every time like it is repeating. Like if you think a bit about this as a wave, the peaks and the valleys, or the crests, like they kind of shrink in size. Is that making sense? So, if you were trying to surf on this wave, it's kind of like a very boring wave, because it continues to get flatter and flatter, right? So if I asked you for the limit as theta goes to infinity, or x of sine of theta over theta, what do you think the limit should be? Now when we go this to infinity. For the orange one. It should be 0 good, because it seems like the peaks of this function keep getting smaller and smaller. So that's where we're going precisely to show using the squeeze theorem. Okay, so let me see if I can go back to the iPad. So just to write what we were saying, so this limit does not exist for just sine of theta. So this means does not exist. This is like a shorthand for saying does not exist. And the reason why this does not exist, because sine of theta oscillates continuously forever, or it oscillates endlessly between -1 and 1 as theta increases. Okay, but what I'm going to claim now, but let's see. Actually, let me use this color. but the limit as theta goes to infinity of sine of theta over theta is going to be 0. That's my claim. Okay. So why? So let's look at sine of theta over theta, right? So a couple of minutes ago, I told you that there's like a very important inequality that sine of theta satisfies. So if you look at that inequality, maybe you wrote it down. What's the biggest sine of theta can be? And I have said this a couple of times already. But so what's the biggest sine of theta can become? Sine of theta can be at most 1, right? So this thing, sine of theta over theta, right, can be at most 1 over theta. Is that making sense? So we know that the numerator, the most it can be is 1. So whatever we have here in the middle, sine of theta over theta, the most it can become is 1 over theta. Is that okay with everyone? And what do you think I could try to put on this left-hand side? So sine of theta is always bigger than a number, right? A number that we know for sure. So what I'm saying is that sine of theta is always less than 1. So in a so since this is always less than 1, you can replace the numerator with 1 in the inequality. And I haven't changed anything else. Um, on the other hand, what could you think I could try to put here? Because we know that sine of theta is bigger than some number all the time, right? So what could I try to put here? Yeah, you could put negative 1 over theta. And why is that? Because sine of theta is always greater than negative 1. Or negative 1 is always less than sine of theta. Is that making sense? Okay, so let me go back to GeoGebra to show you what's going on. Like I should change the colors. So here's sine of theta over theta is like the one we were studying. So then we also have like this function, which is 1 over x or 1 over theta, which is in blue in the picture. Okay, let me call this one G. And we have this function f of x, which is minus 1 over x, or minus 1 over theta, and that's in pink. Okay, so I don't know if you see the squeeze theorem now happening, or the sandwich theorem that I was telling you about, because we have the green one, right? So we have the blue curve, which is above the green curve, and the green curve is above the pink one. So the green curve is always between the blue and the pink one, right? You see, so it's always being squeezed between those two. But the thing is, like, it's easier to understand the limit for the blue and pink ones. So right, so the blue and pink ones are narrowing down. Think of it as kind of walls. That's maybe a better analogy. They're kind of like walls that they start to shrink, right? So since they start shrinking, you leave less space for the green one to navigate, right? So it's kind of like these scary movies where you're running through like a hallway and you see it shrink, and then you're being squeezed between the two things, right? Um, so that's kind of what's happening with the function, if that makes sense. So what I'm saying is that this is a cool thing about the squeeze theorem. So the idea is that it is easier to understand these two limits as theta goes to infinity, because this limit as theta goes to infinity is just zero, right? You're dividing by a very large number. And the limit as theta goes to infinity of the other one, right, of -1 of theta over theta is also just zero. So you see, like the two extremes, like the two walls are going to zero. So that forces the one in the middle to go to zero as well. I mean, you can call it squeeze theorem or sandwich theorem. Either name works. The book uses sandwich, so you can just call it sandwich if you prefer. But I think squeeze theorem is more common. Is that okay? Is that making sense? Any questions about this? Okay. So the next one is also going to be an application of the squeeze theorem, but this one is more tricky. So it's better maybe to do a quick pause for everyone's brains to reset. So let's do like a 5-minute break, and then I'll tell you one that's really important, but it is more complicated. So yeah, this will be on the midterm. Yes, like the stuff for the midterm will be until the start of tomorrow. Yeah, yeah. So tomorrow will be the last day for material for the midterm. I'll be done with what I wanted to include. I'll tell you what's going to be in the midterm uh, by tomorrow, the latest. But yes, it will be in the midterm. Mhm.
Could you explain the limit you have written out on the bottom in green?
Right. So the thing is, like, you see, like the blue and the pink ones are going to zero, right? Is that making sense?
Yes, is the green one the green one's the middle, what you're trying to
Right.
find? Yeah.
Right.
All right.
The green one is the one that I'm trying to find, but since I know that the endpoints or the extreme ones are going to zero, and the green one is somewhere between those two, that forces the one in the middle to go to zero as well. Is that making sense?
Yeah. Thanks.
Yeah, no, like this quiz theorem is kind of like one of the trickiest parts of this limit topic. So we have to do a couple of examples. So yeah, let's start. Let's still do like this 5-minute break. And then I'll tell you a slightly more complicated one, and then we can do some more examples with quiz theorem. Okay, so let me pause this briefly. Okay. Let's see if everyone can hear me. So yeah, let's move. The next one is another application of the squeeze theorem. This one is more tricky. The proof is like a proof, kind of one of those things that we see one time in your you'll see one time in your life. But like the proof itself, you don't have to worry about the proof in the sense that you won't be asked to show it, but it's still like a useful proof to know like at least to understand where it comes from and to give like a different flavor for some of these like um limits, sometimes how you can find a limit. So it's kind of still nice to see what it is all about. But it's not like a proof like that I would expect you to kind of to be able to write down on the exam or anything like that. It's more like for you to like more like a proof to understand what's happening kind of thing. So let me it's still a nice one. It's very elegant, so it's cool to just see it at least once, I feel. Okay. So here's like the next proof. Or the next limit. So if you remember, let me go back to GeoGebra. Where do I have it? Oh, here you are. So if you remember on GeoGebra, so we saw that the limit as theta goes to infinity, right? I can erase this. The limit as theta goes to infinity of this thing is just zero, right? That's what we saw with the squeeze theorem. Now the other limit that involves sine of theta over theta or sine of x over x is the one where theta goes to zero. So before we were looking at the limit when theta went to infinity, right? But now I'm looking at the limit when theta goes to zero. And if you move theta to zero, it does look like this limit should be one. Is that making sense? Based on what the graph looks like. And so we are going to prove that right now. So let me write this down. So this is an important limit. Yeah. Which is the limit as theta goes to zero of sine of theta over theta equals one. Okay. Uh, like the reason why this is kind of tricky, is that as theta goes to zero, the denominator is becoming like zero, right? Because this is zero, and sine of zero is also zero, right? So this is kind of like these limits that we have been seeing in the past, like which is like zero over zero. And the problem is that whenever you run into zero over zero, the answer is not so clear. So that means that you have to do some more work to figure out the answer, if that makes sense. So it's not something where you can just plug in and find the answer. That's what I'm trying to say. You have actually to think about it a little bit more carefully. Okay, so let me show you how the proof goes. It's actually using the squeeze theorem. And for that, we have to draw a couple of pictures here. So I'm going to draw let's see, yeah. Like I'm going to draw 3 copies of the unit circle. see.
Should we know the proofs behind them?
This proof you don't need to know this proof behind this one. For the other one you do because that's like a more normal argument. But for this one, yeah, you don't have to worry about the proof. I'll just show it to you because it's like a nice proof to understand, but it's not like one that I would ask you to, reconstruct. That's what I mean. If that makes sense. So yeah, it's more like to understand why this limit is what it is, but it's not like a proof that I'm expecting you to know. So it's kind of like more like an illustration, like appreciation of how these limits work, kind of thing. So I'm going to draw the unit circle. Okay. Let's say this is an angle theta. Maybe it's easier if I just like I don't know how many ones I want to draw, but okay. So this is going to be the unit circle. Okay. Yeah, you just have to be careful here, like to choose the colors right and things like that to make it easier to understand. Okay, yeah. Okay, so yeah, I'm just trying to do this carefully to not create like a lot of confusion. So let me copy this. I'm going to copy it twice. So the argument, like, is kind of like a very interesting observation, but like, I mean, this one, like, is very clever. Not like one that you would definitely be expected to know how to do or anything like that. But the argument is just saying that the area, right? Do you see that I'm coloring here like a circular sector? So I'm going to use different colors to make it easier. So the argument is just saying that the area of this purple sector is less or equal, right? Than the area of this triangle. Let's see what's a nice color. Let's see. I like orange. Okay, first maybe I should stop. Uh, everyone is convinced that the area of the purple region should be less than the area of the orange region. Hopefully, that looks plausible, right? Because one is inside the other, right? Um, so what I'm saying is that the area of the purple sector or the purple circular sector should be less than the area of the orange triangle, and that should be less than the area of this other sector. Oops, sorry. Area blue sector. Is that making sense? Like everyone believes this? Okay, so let me write it like here. So area purple sector, area blue sector, and area orange triangle, right? So what I'm saying is that we have these inequalities. Is that making sense? And so hopefully you'll see that this will take the shape more of a squeeze theorem in a second. But it is kind of like finding some interesting inequalities between certain areas. Okay. Okay, so let's start with the one in the middle because maybe you remember the area of a triangle more easily. So what's the formula for the area of a triangle? One half base times height. Good, I agree with you. So what's the base in this triangle? What's the formula for the base of this triangle? Excellent, that's cosine of theta, perfect. What's the height of this triangle? It's sine of theta, good. So the area of the triangle should be 1/2 cosine of theta, sine of theta. Is that making sense? Everyone good with this? Any questions up to this point? Again, it's like a derivation. It's not like a proof that I would expect you to know how to do every time, but it's still good to try to understand it, even if not, I'm not going to ask you for it. So okay, now what's the area of the blue sector? Anyone remembers that I gave you like a formula yesterday for the area of a circular sector? Anyone copy that? If not, I can just go back and show it to you. I'll probably do that in a second, but anyone has it written down for what's the area of a sector? Yeah, good. So if you go like let's just scroll back, going to the past. Perfect. Yeah, here you go. So the area of a sector was r squared theta over 2. Perfect. So for the blue one, right? For the blue one, what's the radius of here? What's the radius of this circle? Is a unit circle, right? So r equals 1 in this case. So what's the formula for the area is 1 squared times theta over 2. Is that making sense? And let's go to the purple sector. The purple sector there's still like a formula for the area of a sector that you can use, but now the radius is different, right? Like the radius is not r equals 1, right? What's the radius of this piece of the circle that I'm drawing? What would be the radius? What do you think is the radius? It's smaller, right? It's smaller than 1. I don't know if you can see me draw the. You kind of like the answer is kind of written below. In the picture below. It's cosine of theta. Good. So if this is a radius cosine of theta, this is cosine square of theta times theta over 2. Is that making sense? So that's this is actually almost an inequality that we want. So what could you do in this inequality? You can divide every side of the inequality by theta. So what happens with the left-hand side? It becomes cosine square of theta over 2 less or equal to cosine of theta sine of theta over 2 theta. And this one is less or equal than, if you divide every side by theta, this other side just becomes 1/2. And what else could you do to simplify this inequality? You could multiply by 2, right? Let's multiply by 2. So you get cosine square of theta less or equal than cosine of theta sine of theta over theta less or equal to 1. Okay. And what's the limit that I care about? The limit that I care about was sine of theta over theta, right? So that's almost what we have in the middle. It's just that in the middle, we still have this annoying cosine. So you can divide by cosine of theta on every side of the inequality. Okay. So what do you think is the limit as theta goes to 0 of cosine of theta? It's just one, yeah, because cosine of zero is one, basically. Um, and then what is the limit as theta goes to zero of one over cosine of theta? Oh, it's one over cosine of zero, and that's just. So do you see what's going on here? This side has limit one, this side has limit one as theta goes to zero. And so by the squeeze theorem, the one in the middle must have limit one as well. Is that making sense? Again, it's like a very tricky limit, so that's why I'm general. I'm not expecting you to know how to do this one, this particular one. You definitely need to know this. You must know this limit for sure, like the answer, but you don't need to know the procedure because the procedure is kind of complicated. But it's like still like an interesting limit to go through, just because like it kind of depends a lot on inequalities involving areas. So that kind of gives you like an idea that sometimes like the limits can be found in interesting ways, which are not just like completely algebraic, like factorizing or multiplying by conjugates or things like that. Actually, you can find sometimes limits using more clever things, like for example, like computing some areas and getting some inequalities, and then you can put to work using the squeeze theorem. So it's kind of like a good. I mean, I like it because of, in particular, because of that, because it just kind of like maybe break some stereotypes on what you think could be like how you are supposed to find like limits or what or things like that. Okay, now before the quiz, in the remaining minutes, let me just do some applications of this. Once you have this limit, it's kind of like opening a door to a bunch of new limits you can compute involving trig stuff. So this is kind of like opening Pandora's box. You can like just start like solving a lot of new problems thanks to this limit. So let me do some examples where this limit is applied. So the first one would be the limit as theta goes to zero of tangent of theta over theta. So anyone remembers what tangent of theta is? What was tangent of theta? Tangent of theta was sine of theta over cosine of theta. Yes. So this is an important one to remember. So it is many times, like this is an important trick. Many times when you see trig functions, uh, all the trig functions that matter in the world kind of are always built from sine and cosine. So sometimes to find the limits, it's convenient to kind of write them down in terms of sine and cosine, if that makes sense. Okay. So I don't know now if it looks clear, if there's like anyone has an idea of how you could like find this limit taking advantage of the one we just like taking advantage of this limit. What could you do now? Any guesses? Yeah, good. So we have to use you can right. You basically have to use a limit. You can use the limit loss. So you can see this as a product. So you can think of this as the limit as theta goes to 0 of sine of theta over theta times the limit as theta goes to 0 of 1 over cosine of theta. And the reason why this is useful is because each of these individually, you know what they are, right? You know each of these two limits. Because we already saw that this one is 1, right? And I mean, we have discussed this before. This is 1 over cosine of 0, which is also 1. So you get 1 times 1. So this limit is 1. Is that making sense? Any questions about this limit? Okay, let's maybe do one more before finishing and moving to the quiz. This is another one which is very important limit. So I'll write it down like in a separate box. So here, let's try to find. I'll give you like a chance to think about it. Okay, so I'll give you like 2 minutes to think about it, and then we'll discuss it. But like the idea here is to multiply by the conjugate. The conjugate here is 1 plus, like the conjugate, by that I mean the conjugate of the numerator. Okay. So yeah, I'll give you like 2 minutes and then we'll discuss it. So any ideas? Anyone was able to find the limit? What should this limit be? Well, let's multiply by the conjugate to see what we get. What do you get? What does the numerator become? If you do 1 minus cosine of theta times 1 plus cosine of theta, what is that equal to? Good. 1 minus cosine square of theta. I agree with both of you. Okay. And here you have theta times 1 plus cosine of theta. So far, so good. Now, here's another important identity. There's an identity for what 1 minus cosine square is. Anyone remembers this? Actually, it's related to the one that I wrote last time, yesterday. Yeah, remember that 1 equals sine squared of theta plus cosine squared of theta, right? So 1 minus cosine squared is sine squared of theta. Is that making sense? And now what I'm going to do is kind of break it down like this limit. I'll break it down similarly to the one we had before. So we do have to limit the value for sine of theta over theta. So I'll just take a sine of theta upstairs in the numerator and combine it with the theta below. So I'll write this as the limit as theta goes to 0 of sine of theta over theta times the limit as theta goes to 0 of sine of theta over 1 plus cosine of theta. Is that making sense? So notice that if you multiply this times this, you get sine squared, and you multiply this by this, you get the denominator. So this is fine. It's just that I'm breaking it in a smart way in terms of two limits where I can easily understand the value for each individual limit. Because like the way, if you just write it this way, the problem is with having it this way is that if you just try to plug in theta with 0, you get sine square of 0, which is 0. So you get 0 here, and then there's a 0 here. So you get like 0 over 0. So that's why you cannot just like try to evaluate the limit directly here. You need to break it down into pieces first so that it becomes manageable. Is that making sense? Oh, it's just that to get the blue part, you have to use this identity that 1 equals sine squared plus cosine squared. So if you subtract cosine squared on both sides of this equality, 1 minus cosine squared becomes sine squared. So this is like yeah, this is an identity that everyone should remember as well. Okay, so this limit is 0, and again, this is also a very useful limit to keep around. So I'll write it like in a box for you. The limit as theta goes to 0 of 1 minus cosine of theta over theta is 0. Okay, so this one together with sine of theta over theta are kind of like two of the most important limits involving trig stuff. Is that okay? Is that making sense? Any questions about this? Okay, so let me go back to Canvas. You could also have done the identity in the beginning instead of like doing the conjugate. Yes, like there are other ways to do this limit. Yeah, there are different alternatives. Okay, let me stop sharing this. So again, just for the quiz, remember, so there's going to be there's this quiz, where you'll find the problems. I'm about to make it available, and then there's this second quiz where you will upload the solutions to the problems. This is actually the one that I will be grading. So don't forget to upload the solutions. The other thing I was going to say is that, yeah, when you take the quiz through Respondus, just don't forget to, once you turn it on, like the camera and everything, to try to make the camera like look more towards like your desk space rather than your faces, as I was saying yesterday. Of course, like if you have to move the camera around, um, well, if someone didn't upload the solutions, you can just contact me about that. But yeah, you should always upload the solutions on every time. So, but yeah, if someone forgot last time, you can email me. But in general, do not forget about this. You have 15 minutes after finishing the quiz to upload the solutions. So yeah, so just try to like make the camera show the majority of the time your workspace, and if you have to move it around to just see the problems on the screen, that's fine. But just try to keep it more like closer to what's happening on your table. Okay, so I'll just make these two things available. So feel free to work on. You can start working on them now if you want. So you can leave the Zoom meeting, and I'll see you tomorrow with some new stuff.
Professor, I was gonna come to office hours. Are those gonna happen after the quiz?
Yeah, I'll still be here like around 3, kind of. Yeah.
And we just have to do the quiz by 3 p.m. and it's 15 minutes.
I mean, like it is kind of like the quiz itself is 20 minutes, and
All
then you
right.
have 15 to upload everything.
All right.
So
All
yeah,
right.
I
I'll just do
think
it now.
yeah. Good.
Cool.
See you soon.